This lesson is about Lewis structure and molecular structure. So let's start talking a little bit about chemical bonds before we talk about Lewis structure and molecular structures. We've been working on ionic bonds, and in this image you see two atoms where one atom has the electron all to itself while the other atom no longer has the electron. And so we've been working with atoms where one loses the electron while the other gains the electron. In a covalent bond, these are new bonds that we haven't talked about yet. Those are when two atoms actually share their bonds. So the question is, why would one atom want to lose its bond, lose its electron, and the other one gain it, where the other atoms just want to share them? And that all depends on something called electronegativity. Okay, so whether an atom loses, gains, or shares an electron depends on its electronegativity. And a fancy word for it's a fancy word, but really essentially what it means is it's a measurement of how likely an atom will attract an electron. So let's start with just looking at the periodic table, and we'll start just pretty straightforward. Let's say we are looking at beryllium right over here. And I think for all of us, we recognize beryllium has two valence electrons. And then let's compare that to oxygen. Oxygen, as we know, has 6 valence electrons. Now remember, electronegativity is the likelihood that it's going to attract or gain electrons. Well, if you compare beryllium with oxygen, most of you guys already know that beryllium is not going to be attracting 6 electrons, but the oxygen is more likely to attract those 2 electrons because attracting 2 electrons is a lot easier than attracting 6 of them. So we've already sort of worked with electronegativity. Now, why would an oxygen attract 2 electrons more easily than beryllium? Well, firstly, because remember, oxygen has more protons. That means you have more positive charges. And because you have more positive charges, those electrons are attracted to it much more. So that could be a reason why you have one atom being more electronegative than the other, is that it has more protons, and so it can pull those electrons closer to it. Oxygen has more protons than beryllium does. There's another situation where you have, as you notice, we're looking at oxygen over here, but then we're looking at sulfur down here. And you notice by the number that oxygen is more electronegative than sulfur is. So let's take a look at oxygen. Oxygen, I'm going to draw a very rudimentary Bohr diagram. I'm not putting in all the dots. Okay, and you might remember that oxygen has 2 shells, and because it has 2 shells, remember that the nucleus is kind of buried with 2 layers of protection. Remember that positive nucleus right in here, it's positive, has a shell of 2 negatives, okay? If I have an electron over here, that positive nucleus is going to have to attract between these shells to pull that electron in. So it can definitely do that. But if you were to compare that, so that's our oxygen, if you were to compare that with the sulfur, sulfur doesn't just have 2 shells. Sulfur has 3 shells. There we go. So if I have an electron out here, my positive nucleus here, how likely, which is more likely to attract those electrons? Is it oxygen or sulfur? Well, sulfur, remember, does have that positive charged nucleus, but there are 3 layers of negative electrons shells here. And so for that reason, it's less likely to attract an electron. And that's why you have a number of 2.5 compared to oxygen that only has 2 shells. And that means that this electron can feel more the pull of that positive nucleus because there are less shells. In other words, what we've talked about, a less electron shielding. All right, now in a situation, what happens when we have two atoms that are very similar in electronegativity? So in this case, let me clear my screen. What happens if I have nitrogen and oxygen? So you notice their numbers are very similar. One has a value of 3 electronegativity, the other oxygen 3.5. Just as a reminder, so you can take a look at it, remember nitrogen has 5 valence electrons, oxygen has 6. In this case, you already see the problem. Is it going to be that one wants to pull all the electrons away from the other, or would it make more sense to share them to get that full valence shell? And the answer is it's actually easier to share them. All right, so let's review a little bit about ionic bonds, and then I'm going to introduce covalent bonds. So we've learned that ionic bonds are ones where you have a great difference in electronegativity. I use the example of beryllium and oxygen. Beryllium has, I believe, 4 protons, where oxygen has 8, and that means that those 8 protons can pull those atoms, those electrons closer to it. There is a bigger difference in electronegativity. And so for that reason, you're going to have the beryllium lose the electron while the oxygen gains it. The easiest way to remember it is that nonmetals tend to always, I apologize, let me change that instantly. Nonmetals always are going to bond with metals, okay? Please make that difference. Nonmetals bond with metals, okay? That's an ionic compound, and the reason is that their electronegativity is so different. In terms of covalent bonds, or my apologies, that's an ionic bond called, and they form ionic compounds. If you have covalent bonds, that's the ones where I just talked about nitrogen and oxygen. The number of protons they have is pretty similar. They also have valence shells that don't really make it that easy to sort of lose and gain, and so they will tend to share electrons. And my apologies here again, that is when you have a nonmetal with a nonmetal. And we call those molecules. I know that people normally in everyday life would be like, oh, you're learning about molecules in chemistry and they mean everything. The answer is it's only considered a molecule if it has a covalent bond. So molecules only have covalent bonds. Just make sure to make that change, that it is a non-metal, usually with a non-metal. And the reason is those they have similar electronegativities. So when they bond, there is a very unique way of how they bond, and we use the skills we've learned all along in class to do that. So we're going to start off with H2. You have 2 H's. Remember, we were talking about when they are similar to each other, and you could not be more similar when you are the same element, they will tend to share electrons because their difference in electronegativity is pretty much nothing. All right, so in that case, I have this hydrogen with 1 electron and the other hydrogen with 1 electron. And what they're going to do is, remember, hydrogen just has 1 shell. All it wants to have, remember, in the first shell are 2 electrons. It cannot hold 8 electrons because it's just too small. And so we show that they are sharing electrons by putting a circle around them. This hydrogen has the 2 electrons that it wants, and this hydrogen wants its 2 electrons, has the 2 electrons it wants. When we have 2 dots, it means that those 2 dots form what we call a bond, and we show that bond by drawing a straight line. So this here is the dot structure. The Lewis structure, I'm going to just redraw it, is that dot diagram with those circles showing how they share that. And the molecular structure is where we take those 2 dots and we create a line instead. So this would be the molecular structure of hydrogen. I'm going to skip the lone pairs for right now so that you can actually see an example with lone pairs for it to make more sense. So now let's try chlorine. Again, both of chlorine, if you have two chlorines, these are two non-metals. So we know that they are going to form a covalent bond. Obviously, their electronegativities are going to be the same because it's the same chemical. And the way that I like to see it, and this is why I've always been such a stickler that you draw these dots correctly, wherever you see a location where you just have one dot, that's the place where bonding can happen. So right over here is a place that you can have bonding happen, and right over here is a place where you can have bonding happen. So these chlorines can bond beautifully together, and we can reshuffle those electrons however we want, in that they share that one bonding site that they have. And so remember, the magic number is 8. That allows these chlorines to each have 8 electrons because they share that one electron, which was that single electron. Now we're going to draw the molecular structure. Wherever I have 2 dots with 2 atoms attached to it, I'm going to draw a line, but I cannot forget what we call those other electron pairs, and we call those lone pairs. So this is a lone pair, this is a lone pair, this is a lone pair, and they're all alone, not bonded to another atom. So in this case, the number of lone pairs we have are 6 lone pairs. Now, if we look back at hydrogen, hydrogen does not have any lone pairs, right? We only have, hydrogen is not surrounded by electrons because it only has one valence electron. Okay, so let's try another one. So we have carbon, so let's draw our carbon with its valence electrons, and then we have 4 hydrogens. So let's go ahead and draw our 4 hydrogens. Okay, so what I would do is whenever you actually look on how they can be puzzled together, look for the atom that has the most bonding sites. Now, if you take a look at carbon, remember, I was saying wherever there's a region where you just have one electron, that's a potential bonding site. So I have on the top here a potential bonding site. I have on the right a potential bonding site, on the bottom and on the left. Can I attach these hydrogens so that they can all share the electrons? Just a reminder, hydrogen only wants 2 valence electrons. That's the only one that does. The rest of every atom wants 8. Well, in fact, I can. So if I take my carbon, which has the most bonding sites, I can attach a hydrogen over here. That allows the hydrogen to get those 2 valence electrons. I can attach another hydrogen over here. That allows this hydrogen to get the 2 valence electrons. Attach another one here, and then attach the last one over here. All right, so the hydrogen has its 2 valence electrons that it wants. Does the carbon have the 8 valence electrons it wants? And remember, because they're sharing them, we show lines that overlap. And in fact, when we carefully draw a circle around all those valence electrons, carbon does in fact have 8 valence electrons. It has reached that noble gas configuration, or as I say often, nirvana. So remember, wherever I have 2 dots with 2 atoms bonded together, I create a line. And so the molecular structure of my of CH4 looks like this. So let's take a look. Do we have any lone pairs? And the answer is no. We have 0 lone pairs. All right, let's try another one. Let's try CHCl3. So let's draw our dot structures. we have 4 C's, excuse me, 1 C, 1 H, and 3 Cls. So I like to kind of draw them out just to see what I've got going. Remember, I choose the atom that has the most bonding sites in the center, and carbon is always the one that has the most bonding sites. That's why life is made up of carbon, because so many things can bond to it. So I've got a bonding site on the top, both bonding sites on the sides are available, and one on the bottom. I have 4 atoms that can bond with it. I'm going to randomly choose to put hydrogen over here. It's okay if you put hydrogen anywhere else. There's no real reason why I put it on the left. It could be on the top, it could be on the bottom, it could be on the right. And that takes care of my hydrogen. Now I'm going to start putting the chlorine on here. Okay, remember chlorine has 7 valence electrons. So by having the chlorine bonded here to the carbon, it means that this chlorine is able to get its 8 valence electrons that it wants by sharing them with carbon. Hydrogen has the 2 valence electrons that it wants. And let's double check with carbon, making sure that carbon has all the valence electrons. Remember, because they're sharing them, we are overlapping these circles, and it works out beautifully. All right, so now what would the molecular structure look like? Remember, wherever you have 2 dots bonded with 2 different types of atoms, we put a dash, but don't forget the lone pairs. These are going to be really important, especially later on when we can predict on how likely something is going to interact with something else. Okay, so we've got some lone pairs over here. So that means we have, in this case, 3 lone pairs on the top, 3 lone pairs on the second chlorine, and another 3 on the third chlorine. We have 9 lone pairs. Let's do one more as a last one. The last one gets a little bit more complicated. You're going to see that I have 3 carbons. There we are. We have 7 hydrogens. And we have 1 phosphorus. And just a reminder, phosphorus has 5 valence electrons. Okay, remember we always start with the chemical that has the most bonding sites. And so I'm going to go ahead and start with carbon. And now at this point, I can choose to bond it with another carbon, or I can choose to bond it with a phosphorus. The one you want to always choose last is hydrogen. Always, always, I'll write it down, always bond hydrogen last. And the reason is it's the filler, okay? So I am going to choose carbon. So if I have carbon, there we go. I can bond it with another carbon. That works just fine. All right, now I'm going to work with phosphorus. Let me bond phosphorus next. I have 1, 2, 3, 4. Okay, now let's see if it works out that I can bond my different hydrogens. So let me make sure that I have this done correctly. I have 1 hydrogen here. I have a feeling I may have written the structure incorrectly. I think there's a 9 here. And I should actually be drawing dots. There we are. My apologies, you guys. This is just to double check that I'm right. This should be a 9. Okay? There we go. Let me add 2 more hydrogens. All right, so I again check, do my hydrogens have the 2 valence electrons? Yes, they do. And this one it does as well. There we go. Does my phosphorus have the 8 it wants? Yes. Does the carbon have the 8 it wants? Yes. Remember, they're sharing electrons so that they can overlap. There we go. And so the structural formula for this is Okay, so now you could have also said, and it would have been just as accurate, couldn't I bond my phosphorus to this situation? And the answer is yes, I could have gone like this and come up with a different combination, in which case I have another hydrogen here, another hydrogen here, hydrogen here, hydrogen here, hydrogen here, one here, one here, here, and here. I still have 9 hydrogens, but now this structural formula looks even different. So this one could look like C with a P, C, C, and then we have our hydrogens. Oh, and I have to make sure to include that lone pair. Please make sure to make those changes. Don't forget the lone pair. All right, so when I have 2 different options, I say I have 2 isomers, okay? These are different variations. And some chemicals, you can have many different variations, the larger they are. So in this case, it's a large molecule. It has 2 different variations, and remember, I have 1 lone pair.